In subtopic D.2 stellar characteristics and stellar evolution, we're first going to have a look at stellar spectra. In order to do that, though, we need to refer back to subtopic 7.1. And in subtopic 7.1, we looked at emission spectra and absorption spectra. And the reason why they're important here is because they apply equally to stars and allow us to identify certain properties about stars. So just to briefly refresh your memory, those sorts of spectra, if we just look at for hydrogen, so just have a look at what they both look like. So the one on the top is the emission spectrum. So when light is being radiated from hydrogen atoms, they're the four bands of colour that we'd see in the visible spectrum. Keep in mind there is ultraviolet and infrared bands there as well, but we'll just deal with the what we can see. And then down the bottom is the absorption spectrum, where if light was passing through hydrogen gas, it would absorb those four black lines, and equally again ultraviolet and infrared lines as well. Now these spectra, and keep in mind we're not just going to be dealing with hydrogen, they can be used to determine a number of properties of stars, or a number of characteristics. And some of those we'll go through very briefly. Now, I'm not going to go through and talk about a whole lot of the detail here, just sort of a bit of a broad brush overview. So the first thing is that it can tell us about the chemical composition of the stars. So if we were to look at the spectrum from a star, any spikes or dips in a star spectrum can be matched to those of the that we know for known elements. So if we were to see those four bands of light that we just saw for hydrogen, we would then be able to identify that that particular star has hydrogen in it because it's radiating those colours of light that match up with hydrogen. Similarly to that, but in a slightly different way, we can then look at the density of a star as well. So it's a little bit trickier. If we have dips in a star's spectrum, what that usually means is, well, in some cases, usually relate to light being emitted from the hot dense center of the star, being absorbed by gas that's or by cooler, lower density gas. Further out from the core. So light being radiated from inside the star being absorbed by cooler gas that's around the star could show us that there is those gases that are further around the outside of the star, and therefore we can identify that the center of the star is more dense than the outside. The third one that we can talk about is the velocity of the star. Now this one we'll cover in more detail later, but just to briefly mention it here, we can use the Doppler effect or the Doppler shift of those spikes in the spectrum, or those bright bands in the spectrum, and if they have been Doppler shifted, so because the star's moving towards or away from us, we can then identify how fast it is. So if you think about those four bands for hydrogen, they would still be in the same sort of relative position to each other, the relative spacing, but because of Doppler shifting, they'd either be sort of all shifted to the right or all shifted to the left. And as a result, we can then determine how fast the star is moving. And finally, the other property that we'll talk about here is temperature. Now, for temperature, we also need to refer to Unit 8. So if we treat stars as black bodies, so objects that radiate energy across the electromagnetic spectrum, we can use Wien's law to relate the temperature to the wavelength. So a star's surface temperature. And when we're talking wavelength, we're talking about the peak. So it's a bit of a cumbersome one to describe here. Talking about the wavelength that has the maximum intensity. So not the maximum wavelength, the wavelength that has the maximum intensity in the star's blackbody radiation curve. So the equation that we need to be aware of there is that the wavelength that corresponds to the maximum intensity multiplied by the temperature is equal to 2.9 by 10 to the negative 3 meter Kelvin. So that's one of the equations in the in the data booklet. So basically, there you're looking at a inversely proportional relationship. If the wavelength goes up, then the temperature goes down, basically. So there's some of the properties that we can determine by looking at stellar spectra. We can discuss a few more of those in more detail in class to get a much better idea of all the ins and outs of those concepts.